Hello there, and welcome to The Sleepy Astronaut, where wonder meets wandering and the cosmos gently carries us towards slumber. Tonight, we're embarking on a celestial journey to meet a mysterious visitor from beyond our solar system and uncover why space rocks have such a dramatic tendency to vanish into thin air. But before we dive into the depths of interstellar space, I'd love to know where in the world you're listening from tonight and what's the view like outside your window right now. Perhaps you're gazing up at the same stars that have witnessed the birth of distant worlds. Or maybe you're simply settling in for a peaceful exploration of the universe from the comfort of your favourite spot. Either way, you're exactly where you need to be. If you find tonight's cosmic adventure soothing, or simply a delightful way to drift toward dreams, I'd be grateful if you'd give this video a gentle like and perhaps subscribe. It helps this little corner of scientific serenity reach other stargazers who might need a tranquil pause in their evening too. Now, I do hope this tale of interstellar wanderers and atmospheric mysteries isn't so captivating that it keeps you wide awake. But if it does, well, at least you'll have learned something extraordinary about our cosmic neighbourhood before you surrender to sleep. So settle in, let your thoughts slow down, and let's begin, because somewhere between distant star systems and our protective atmosphere lies a story that's both ancient and unfolding right now. Our story begins on a perfectly ordinary morning in July 2025, when astronomers at the Asteroid Terrestrial Impact Last Alert System telescope in Rio Hurtado, Chile, were conducting their usual sweep of the southern sky, searching for potentially dangerous space rocks that might threaten our planet. It was routine work, the kind of methodical observation that happens every clear night at observatories around the world. But on July 1st, something appeared in their images that would change everything they discovered what would soon be confirmed, as only the third known interstellar object ever spotted visiting our solar system. A cosmic wanderer that had been drifting through the galaxy for billions of years before finally crossing paths with our sun. Initially, the astronomers weren't entirely sure what they were looking at. The object designated 3I Atlas seemed unremarkable at first glance. Just another dot of light moving slowly against the background stars, but careful analysis of its trajectory revealed something extraordinary. This wasn't just another asteroid or comet from the outer reaches of our own solar system. This visitor was moving far too fast and in completely the wrong direction to belong to our stellar neighbourhood. It was travelling at an incredible 58 kilometers per second, relative to the Sun, almost twice as fast as the previous interstellar objects we'd encountered. And its path through space told a story of unimaginable distances and cosmic loneliness. Within days of its discovery, follow-up observations revealed even more intriguing details. The object began to show signs of activity, developing a faint, fuzzy atmosphere, or coma around its nucleus, and hints of a tail streaming away from the Sun. This confirmed that 3I Atlas wasn't just a rocky asteroid, but an active comet carrying ancient ices from its birthplace around another star somewhere in the thick disk of our Milky Way galaxy. Imagine, if you will, a snowball that has been wandering through the cosmic deep freeze for eons, preserving within its icy heart the chemical fingerprints of an alien star system. The timing of 3I Atlas discovery couldn't have been more fortuitous for astronomers. This interstellar visitor was approaching the inner solar system during an era when our technological capabilities for studying such objects have never been better. Unlike its predecessors, 1I Oumuamua, which caught us completely off guard in 2017, and 2I Borisov, which gave us only a brief window for observation. 3I Atlas arrival was detected early enough to mount a coordinated international campaign of observations using every available telescope and spacecraft in our arsenal. But here's where our story takes a peculiar turn that connects to one of the most fascinating mysteries in planetary science: the behaviour of objects when they encounter the intense environment near our Sun, and more broadly, the puzzle of why space rocks have such a remarkable tendency to disappear long before they reach the ground. You see, 3I Atlas, despite being a visitor from another star system, is about to demonstrate the same vanishing act that countless meteoroids perform in our atmosphere every single day, As 3I Atlas continues its journey toward its closest approach to the Sun, scheduled for late October 2025, it will gradually disappear from our view, not because it's being destroyed, but because it will become lost in the Sun's glare hidden behind our star until it re-emerges in early December. This celestial game of hide-and-seek mirrors, in many ways, the mysterious fate of the countless meteoroids that enter Earth's atmosphere every day, traveling at tremendous speeds, only to vanish in brilliant flashes of light, leaving behind only fleeting trails and occasionally small fragments. The mystery of disappearing meteoroids has puzzled scientists for generations. Why do objects that survived millions or billions of years in the harsh environment of space, traveling through the cosmic void, suddenly disintegrate so dramatically when they encounter our planet's atmosphere? The answer, as we'll discover, involves some of the most elegant and violent physics in our solar system. A dance between speed pressure and the fundamental properties of matter that plays out thousands of times every day above our heads. Most people imagine that meteoroids simply burn up as they streak through our atmosphere, like cosmic matches being struck against the sky. But the reality is far more complex and fascinating than this simple explanation. Suggests the process of meteoroid disintegration involves an intricate interplay of forces that would make even the most dramatic Hollywood explosion seem tame. By comparison, these space rocks don't just melt away, they undergo a catastrophic transformation that literally tears them apart from the inside out. Consider for a moment what happens when a chunk of rock or metal that has been drifting through the near absolute zero temperature of space suddenly encounters Earth's atmosphere at speeds of at least 11 kilometers per second. That's more than 24,000 miles per hour, fast enough to circle our entire planet. In just over 3.5 hours, the meteoroid isn't just moving quickly through air, it's compressing the atmosphere in front of it to tremendous pressures, creating temperatures that can exceed those found on the surface of the Sun. But here's where the story becomes truly remarkable. Recent computer simulations and theoretical work have revealed a previously unknown mechanism that makes meteoroid disintegration even more dramatic than scientists had realized. As these cosmic visitors hurtle through our atmosphere, the high-pressure air in front of them doesn't just create external heating and ablation, it actually infiltrates the interior of the meteoroid through tiny cracks and pores, creating pockets of superheated high-pressure gas inside the rock itself. Imagine, if you will, trying to blow up a balloon that's already inside another balloon. The internal pressure builds and builds until something has to give in the case of meteoroids. This internal pressure becomes so intense that it literally explodes the object from within, even if the material is strong enough to withstand the external atmospheric forces. This process helps explain why even relatively large and solid meteoroids often disintegrate completely, leaving only tiny fragments to reach the ground. The Chelyabinsk event of February 15, 2013, provides a dramatic real-world example of this process when a 20-meter diameter asteroid exploded 12 miles above Chelyabinsk, Russia. It released energy equivalent to approximately 30 Hiroshima atomic bombs. The resulting shockwave damaged thousands of buildings and injured about 1,500 people. Yet despite its enormous initial mass of over 10,000 metric tons, only about 0.1% of the original object made it to the ground as meteorite fragments. What makes the Chelyabinsk event so scientifically valuable is that it was captured by countless dashboard cameras and security systems throughout the region, providing researchers with unprecedented documentation of how large meteoroids behave during atmospheric entry. The footage reveals not just a single explosion, but a series of fragmentations as the object repeatedly broke apart, each piece continuing to disintegrate until only the smallest, most resilient fragments survived the journey to Earth's surface. But the mystery deepens when we consider that the mechanical strength of the meteoroid during its explosive disintegration was measured to be 2 orders of magnitude lower than the strength of the meteorite fragments that were eventually recovered. This suggests that the process of atmospheric entry doesn't just heat and ablate meteoroids. It fundamentally changes their structural properties, making them far more fragile than they were in the cold vacuum of space. This brings us back to our Interstellar Visitor 3 Eye Atlas, and the broader question of how objects behave when they encounter the intense radiation and gravitational forces near our Sun. As 3i Atlas approaches its October rendezvous with our star, it too will undergo dramatic changes, not unlike the transformations that destroy meteoroids in our atmosphere. The comet's ancient ices will begin to sublimate, transforming directly from solid to vapor and carrying away embedded dust and rocky material in brilliant jets and streams. The Hubble Space Telescope has already captured images of 3i Atlas, showing a teardrop-shaped cocoon of dust streaming away from its nucleus as solar heating begins to take effect. The James Webb Space Telescope has detected unusual concentrations of carbon dioxide water, vapor, carbon monoxide, and other exotic compounds in the comet's growing atmosphere, revealing the chemical fingerprints of its alien birthplace. These observations are particularly precious because they offer us a rare glimpse into the composition of materials that formed under completely different stellar conditions than anything in our own solar system. What makes 3i Atlas especially intriguing is that it began showing signs of activity when it was still more than 6 astronomical units away from the Sun, roughly the distance of Jupiter. This early onset of cometary behavior suggests that the interstellar visitor contains highly volatile materials that can sublimate at much lower temperatures than ordinary water ice-creating activity at distances where most solar system comets remain dormant. As we watch 3i Atlas gradually brighten and develop its characteristic tail, we're witnessing the same fundamental processes that govern meteoroid disintegration, the transformation of solid matter into gas and plasma, the interplay between internal and external pressures, and the delicate balance between structural integrity and the forces trying to tear objects apart. The only difference is one of scale and environment instead of atmospheric entry. We're observing solar approach. Instead of seconds, we're watching months of gradual change. The physics underlying both phenomena share remarkable similarities, whether we're talking about a grain of sand entering our atmosphere at cosmic speeds or an interstellar comet approaching our Sun. The fundamental question remains the same. What happens when matter encounters extreme conditions that push it beyond its structural limits? And why do these encounters so often result in spectacular disintegration rather than gradual erosion? To understand this mystery, we need to venture into the realm of fluid dynamics and material science, where pressure waves and temperature gradients create forces that can literally reshape matter at the molecular level. When a meteoroid enters Earth's atmosphere, it doesn't simply encounter air resistance in the way a falling leaf might. Instead, it creates what scientists call a bow shock, a compressed wave of superheated plasma that forms in front of the object like the wake of a speedboat, but infinitely more violent. The temperatures generated by this compression can reach 15,000 degrees Celsius, hot enough to vaporize any known material. Yet the meteoroid doesn't simply melt away uniformly. Instead, the heating creates tremendous thermal stresses as the outer layers expand, while the interior remains relatively cool. These differential expansion forces can crack even the most solid, rock-creating pathways for the high-pressure plasma to penetrate deep into the meteoroid's structure. Recent computational models have revealed that this process creates what researchers call Rayleigh-Taylor instabilities, beautiful undulating patterns where dense meteoroid material tries to mix with the lighter surrounding plasma. The result is a cascade of fragmentation that starts at the surface and works its way inward, breaking the object into progressively smaller pieces, each of which undergoes its own miniature version of the same destructive process. But perhaps the most elegant aspect of meteoroid disintegration is how it demonstrates the protective power of Earth's atmosphere. What might seem like a violent destructive process is actually our planet's gentle way of shielding us from cosmic bombardment. The same forces that tear apart incoming space rocks ensure that only the smallest, most harmless fragments ever reach the ground where we might encounter them. This atmospheric protection operates on a scale that's almost difficult to comprehend. Every day, Earth encounters roughly 100 tons of cosmic debris, ranging from microscopic dust grains to occasional house-sized boulders. Yet thanks to the complex physics of atmospheric entry, less than 5% of this material survives to reach the surface. And most of what does survive arrives as harmless pebbles, rather than crater-forming projectiles. The process is so effective that even objects the size of automobiles typically disintegrate completely, creating nothing more than spectacular light shows for anyone fortunate enough to witness their final moments. This efficiency stems from the fact that disintegration isn't just about heating. It's about the fundamental mismatch between the extreme conditions of atmospheric entry and the structural properties of materials that formed in the cold vacuum of space. When we observe 3I Atlas through our telescopes, we're seeing this same mismatch playing out on a much larger scale. The comet's nucleus, forged in the frigid environment around another star, is encountering the intense radiation and solar wind of our Sun for the first time in its billion-year journey. The result is a gradual transformation as volatile compounds sublimate away, carrying with them embedded dust and creating the characteristic tail that makes comets so visually striking. The European Space Agency's Mars Express orbiter and NASA's various Mars missions are preparing to observe 3I Atlas during its closest approach to the red planet in early October, providing us with a unique opportunity to study an interstellar object from multiple vantage points simultaneously. This coordinated observation campaign represents one of the most comprehensive studies of any comet in history, let alone one from another star system. What makes these observations particularly valuable is that 3I Atlas is following what astronomers call a hyperbolic trajectory, meaning it will never return to our solar system after completing its current flyby. This is our one and only chance to study this particular messenger from the stars, making every observation precious and irreplaceable. Unlike periodic comets that return every few decades or centuries, 3I Atlas is a once-in-a-lifetime visitor. The comet's chemical composition, as revealed by spectroscopic analysis, tells a story of conditions in its birth system that may have been quite different from our own. The unusual abundance of carbon dioxide relative to water suggests formation in a colder environment, while the presence of exotic compounds like carbonyl sulfide hints at chemical processes that may be rare in our local galactic neighborhood. As 3I Atlas continues its approach toward the Sun, astronomers are watching for signs of the kind of dramatic outbursts that sometimes occur when cometary nuclei undergo rapid structural changes. The famous Comet 17P Holmes provided a spectacular example in 2007, when it suddenly brightened by 15 magnitudes, becoming 1 million times brighter in less than 2 days. The cause of such outbursts remains mysterious, but they may be related to the same kinds of internal pressure buildup that tear apart meteoroids in our atmosphere. The possibility of witnessing such an event in an interstellar comet would provide unprecedented insights into how these ancient objects respond to solar heating. After billions of years in the deep freeze of interstellar space, the structural integrity of 3I Atlas has been tested only by the gentle forces of cosmic ray bombardment and occasional collisions with interstellar dust grains. The intense environment near our Sun represents an entirely new kind of stress test. Meanwhile, the daily meteor showers that grace our night skies continue to demonstrate the same fundamental principles on a smaller scale. Each streak of light represents a cosmic visitor meeting its end in a burst of incandescent plasma. The Leonids, Perseids, Geminids, and dozens of other annual displays are actually the remnants of ancient comets whose orbits periodically intersect Earth's path through space. These meteor streams provide natural laboratories for studying disintegration physics, as astronomers can observe thousands of similar objects undergoing atmospheric entry under controlled conditions. The variations in brightness, duration, and fragmentation patterns reveal details about the internal structure and composition of the parent comets. Some meteors flare briefly and vanish, while others undergo multiple fragmentations, creating spectacular fireball displays. The largest meteoroids, those rare visitors measuring several meters across, create the most dramatic atmospheric entries, often visible in broad daylight and accompanied by sonic booms that can be heard hundreds of kilometers away. These events, like the Chelyabinsk impact, remind us that while Earth's atmosphere provides excellent protection against smaller debris, truly large objects can still occasionally slip through, creating regional effects. The study of these atmospheric entries has practical implications beyond pure scientific curiosity. As our species becomes increasingly dependent on satellite technology and space infrastructure, understanding how objects behave during high-speed atmospheric encounters becomes crucial for protecting our orbital assets. The same physics that governs meteoroid disintegration also applies to space debris and decommissioned satellites returning to Earth. Engineers designing spacecraft heat shields draw heavily on research into meteoroid behavior using similar principles to protect human crews during atmospheric re-entry. The Apollo command modules that brought astronauts safely home from the Moon relied on ablative heat shields that channeled away the intense heating through controlled material loss, much like a meteoroid sacrificing its outer layers to protect its core. But perhaps the most profound implication of meteoroid disintegration research lies in its connection to the broader question of how matter behaves under extreme conditions. The same physical principles that tear apart space rocks operate in stellar atmospheres, planetary formation processes, and even the creation of heavy elements in the hearts of dying stars. The dance between pressure, temperature, and structural integrity that we observe in meteoroid disintegration is a fundamental aspect of how the universe shapes and reshapes matter, from the quantum scale to the cosmic scale. Every atom in our bodies was once part of a star that underwent its own version of catastrophic disintegration, scattering the elements of life across the galaxy, where they eventually found their way into planets, atmospheres, and ultimately into us. As 3I Atlas continues its stately progression through our solar system, carrying within its ancient nucleus the chemical memory of another star, we're reminded that we too are made of cosmic wanderers, atoms that have travelled unimaginable distances through space and time to briefly come together in the form of conscious beings, capable of contemplating our own origins. The story of 3I Atlas becomes even more captivating when we consider the sheer improbability of its discovery. Wandering through the vast emptiness between stars, this cosmic nomad has been drifting for perhaps hundreds of millions of years through a galaxy containing 400 billion stars. Yet somehow, it found its way into our tiny corner of the Milky Way at precisely the moment when humanity has developed the technology to detect and study it. The odds of such a convergence are so astronomically small that it feels almost like a carefully orchestrated cosmic appointment. But 3I Atlas is far from alone in its journey through our solar system every day. Our planet encounters thousands of smaller interstellar visitors, microscopic dust grains that have been expelled from dying stars, supernovae and stellar winds. These tiny messengers carry within their crystalline structures the chemical signatures of processes that occurred light years away and eons ago. Yet they arrive so quietly that we barely notice their presence settling gently into our upper atmosphere, where they become part of Earth's own cosmic dust collection. The contrast between these silent arrivals and the spectacular demise of larger meteoroids reveals something profound about the relationship between size, speed, and survival in space environments. The smallest particles, those measuring mere micrometers across, can drift through our atmosphere almost undisturbed, their tiny mass, insufficient to generate the catastrophic heating that destroys their larger cousins. Meanwhile, objects in the middle, range from pebbles to boulders, face the most violent fate caught in a deadly sweet spot, where they're too large to slip through unnoticed, but too small to survive the encounter intact. This size-dependent survival creates what scientists call the meteoroid paradox, the objects most likely to survive. Atmospheric entry are either vanishingly small or extraordinarily large with very little middle ground. The tiniest dust grains float down like cosmic snow. While only the most massive asteroids have enough structural integrity and thermal mass to punch through our atmospheric shield, relatively intact, everything in between faces almost certain disintegration. The physics behind this paradox lies in the scaling relationships that govern how objects interact with fluid environments. As size increases, surface area grows as the square of the linear dimension, while volume and mass increase as the cube. This means that larger objects have proportionally less surface area exposed to atmospheric heating relative to their thermal mass, allowing their interiors to remain relatively cool even as their surfaces ablate away. But there's another factor at play here, one that connects directly to the mystery of why some objects seem to vanish more completely than others. The internal structure of meteoroids varies dramatically depending on their origin and history. Some are solid chunks of metal or rock forged in the cores of asteroids, while others are loosely bound aggregates of dust and ice, more akin to dirty snowballs. These structural differences profoundly influence how objects respond to the stresses of atmospheric entry. Consider the difference between a solid iron meteoroid and a carbonaceous chondrite, rich in volatile compounds. The iron meteoroid, with its dense crystalline structure, might survive atmospheric heating long enough to create a substantial crater, while the carbonaceous chondrite could disintegrate so completely that it leaves behind only a brief flash of light and a handful of microscopic particles scattered across hundreds of square kilometers. This structural diversity reflects the complex history of our solar system, where different regions and different epochs have produced materials with vastly different properties. The asteroid belt between Mars and Jupiter contains objects that formed under relatively gentle conditions, preserving primitive materials from the solar nebula. Meanwhile, meteoroids originating from the Moon or Mars carry the scars of massive impact events that shattered and reformed their parent bodies multiple times. 3I Atlas brings yet another layer of complexity to this story. As an object that formed not just in a different part of space, but around an entirely different star. The conditions in its birth system, the temperature, pressure, and chemical environment that shaped its nucleus may have been unlike anything we've encountered in solar system materials. This makes every observation of the comet precious, not just for what it tells us about interstellar objects, but for how it expands our understanding of planetary formation processes throughout the galaxy. The James Webb Space Telescope's spectroscopic analysis of 3I Atlas has already revealed tantalizing hints of this alien chemistry. The unusually high concentration of carbon dioxide suggests formation in a region where carbon monoxide ice could condense something that occurs only in very cold environments, well beyond the snow line of most star systems. Meanwhile, the presence of complex organic compounds hints at chemical processes that may have operated differently under the radiation environment of another star. As the comet continues its approach toward the Sun, these exotic compounds are beginning to sublimate away, creating a growing atmosphere that serves as a natural laboratory for studying interstellar chemistry. The gas and dust streaming away from the nucleus carry with them the molecular fingerprints of processes that occurred billions of years ago in a stellar system that may no longer even exist. The European Space Agency's Mars missions are uniquely positioned to observe this transformation, as 3I Atlas passes close to the red planet in early October. The perspective from Mars will provide views of the comet's sunward side, unavailable from Earth-based telescopes, potentially revealing details about how the nucleus responds to intense solar heating. The HOPE spacecraft's Emirates Mars ultraviolet spectrometer will be particularly valuable for detecting the characteristic signatures of water vapor and other volatile compounds as they stream away from the comet's surface. Meanwhile, back on Earth, ground-based observatories are racing against time to capture as much data as possible before 3I Atlas disappears behind the sun's glare. The comet will remain visible through the end of September, after which it will be lost to observers until it re-emerges in early December. By then, it will have undergone its closest approach to the Sun and may have changed dramatically depending on how its ancient ices respond to unprecedented heating. This disappearing act mirrors the fate of countless meteoroids that enter our atmosphere every day, visible for only brief moments before vanishing forever. But while meteoroids disappear through violent disintegration, 3I Atlas will simply slip behind the overwhelming brightness of our star, a cosmic magic trick that leaves us wondering what transformations might be occurring during its hidden passage. The anticipation surrounding the comet's reappearance in December has astronomers planning observation campaigns months in advance. Will 3I Atlas emerge relatively unchanged from its solar encounter? Or will it have undergone one of the dramatic outbursts that sometimes transform comets beyond recognition? The answer lies hidden in the complex interplay between the comet's internal structure and the intense environment it's about to encounter. This uncertainty reflects a deeper mystery about how objects from interstellar space respond to conditions in our solar system. 3I Atlas has spent billions of years in the near absolute zero temperature of the cosmic void, where chemical processes virtually cease and structural changes occur only on geological timescales. The sudden exposure to solar radiation represents a shock to its system that could trigger cascading changes throughout its nucleus. The same thermal stresses that tear apart meteoroids in our atmosphere operate on cometary nuclei as well, but on much longer timescales. Instead of seconds of heating, followed by destruction, comets experience months or years of gradually intensifying solar radiation that slowly works its way into their interiors. The result can be spectacular outgassing events that create temporary atmospheres larger than some planets. Hubble's images of 3I Atlas already show clear evidence of this process, beginning with dust streams and a developing tail that grows longer and more pronounced. With each passing week, the teardrop-shaped coma surrounding the nucleus reveals the direction of the solar wind as it sweeps away the sublimating gases and embedded dust particles, creating the characteristic appearance that has fascinated humans since ancient times. But the most intriguing aspect of 3I Atlas may be what happens after its closest approach to the Sun. As the comet swings around our star and begins its journey back toward the outer solar system and eventually into the depths of interstellar space, it will carry with it a transformed surface and possibly a completely altered internal structure. The solar heating will have penetrated deep into its nucleus, potentially changing the distribution of volatile compounds and creating new pathways for future outgassing. This transformation process offers a unique window into how comets evolve over cosmic timescales. While most comets in our solar system have undergone multiple passages near the Sun, gradually losing their most volatile components, 3I Atlas is experiencing solar heating for the first time in its multi-billion-year existence. The changes we observe may represent the initial stages of cometary evolution, a process we rarely get to witness in such pristine form. The connection between cometary evolution and meteoroid disintegration becomes clearer when we consider that many meteor showers originate from the debris trails left by comets during their repeated passages through the inner solar system. Each time a comet approaches the Sun, it sheds material that continues to follow the comet's orbital path, creating streams of particles that Earth encounters on a predictable schedule. The Perseids, for example, originate from Comet Swift-Tuttle, which last passed through the inner solar system in 1992, leaving behind a trail of debris that produces spectacular meteor displays. Every August, when Earth passes through this stream, we're essentially witnessing the delayed disintegration of material that was once part of the comet's nucleus, transformed by solar heating into a cloud of particles that now create fleeting streaks of light in our night sky. 3I Atlas will never contribute to such a display because its hyperbolic trajectory ensures it will never return to our solar system. But the material it's currently shedding will continue to orbit the Sun for millions of years, gradually spreading throughout the inner solar system. Some of this interstellar dust may eventually find its way to Earth, where it will join the constant rain of cosmic particles that settles into our atmosphere. The study of this interstellar material represents one of the most exciting frontiers in planetary science because it offers direct access to samples from other star systems, without the need for interstellar travel missions. The dust grains streaming away from 3I Atlas carry within their atomic structure information about conditions in the comet's birth system, including isotopic ratios that can reveal details about stellar nucleosynthesis processes and the chemical evolution of the galaxy. Advanced mass spectrometry techniques can already detect individual interstellar dust grains in samples collected from the upper atmosphere and from spacecraft missions like Stardust, which captured particles from Comet Weil 2. The challenge lies in distinguishing truly interstellar material from the overwhelming background of solar system dust. But the unique isotopic signatures of interstellar grains make them identifiable to researchers with the right analytical tools. As 3I Atlas continues to brighten and develop its characteristic tail, the comet is essentially conducting a controlled experiment in matter transformation under extreme conditions. The same physical principles that govern meteoroid disintegration operate here, but at a pace that allows us to observe and study each stage of the process in unprecedented detail. The gradual nature of cometary evolution stands in stark contrast to the violent, instantaneous destruction of meteoroids, yet both phenomena spring from the same fundamental physics, the interaction between matter and energy under conditions far removed from the gentle environments where these objects originally formed. Whether we're watching a grain of sand incinerate in our atmosphere, or an interstellar comet slowly transform under solar heating, we're witnessing the universe's ongoing project of breaking down and rebuilding matter in an endless cycle of creation and destruction. This cosmic recycling process connects 3I Atlas to every meteoroid that has ever streaked across our sky, and to every atom that makes up our planet and our bodies. The calcium in our bones may once have been part of an asteroid that disintegrated in Earth's early atmosphere billions of years ago, while the carbon in our DNA could have arrived aboard an interstellar comet, not unlike the one we're watching today. The poetry of this connection becomes even more profound when we realize that 3I Atlas itself is made of recycled stellar material forged in the nuclear furnaces of stars that died long before our sun was born. The comet's nucleus contains heavy elements that could only have been created through the violent deaths of massive stars, their final explosive moments scattering the ingredients for future worlds across the galaxy. As we prepare for 3I Atlas to slip behind the sun and temporarily vanish from our view, we're reminded that disappearance and reappearance are fundamental themes in cosmic evolution. Stars are born from collapsing gas clouds, shine for billions of years, and then fade or explode, scattering their material to begin the cycle. And new comets emerge from the outer darkness, approach the warmth of stars, and then retreat again, carrying with them the memory of their brief illumination. The meteoroids that grace our night skies with their final brilliant moments are participating in this same eternal dance, arriving from the cold depths of space to meet their end in a blaze of light that briefly outshines the stars themselves. Their disintegration is not truly an ending, but a transformation, releasing energy and returning material to the cosmic cycle that will eventually build new worlds and perhaps new forms of life. In this context, the mystery of disappearing meteoroids becomes less about destruction and more about change. These cosmic visitors don't simply vanish. They transform from solid matter into energy and plasma, contributing their substance to the very atmosphere that protects our planet. The same atmosphere that allows us to breathe and live and contemplate the wonders of the universe. As 3I Atlas prepares for its own transformation, during its hidden passage behind the sun, we can only wait and wonder what changes this ancient wanderer will undergo in the intense radiation environment near our star. Will it emerge in December as the same object that disappeared in September? Or will solar heating have fundamentally altered its character, creating new jets of gas and dust that reveal previously hidden layers of its nucleus? The answer to this question lies hidden in the delicate physics of sublimation, the process by which solid ice transforms directly into vapor without ever becoming liquid. This phenomenon, which occurs routinely in your freezer when ice cubes slowly shrink over time, becomes dramatically amplified in the vacuum of space, where the absence of atmospheric pressure allows ice to sublimate at temperatures far below what we experience on Earth. When 3I Atlas was drifting through the cosmic deep, its nucleus remained in a state of perfect preservation, locked in temperatures approaching absolute zero, where molecular motion nearly ceases. The various ices within its structure, water certainly, but also carbon monoxide, carbon dioxide, and more exotic compounds, existed in a kind of suspended animation, their crystalline lattices unchanged for geological ages. But as our interstellar visitor begins to feel the growing warmth of our sun, these ancient ices are awakening from their billion-year slumber. The process doesn't happen all at once, mind you. Different compounds sublimate at different temperatures, creating a layered response as solar heating gradually penetrates into the comet's interior. The most volatile substances, those exotic ices that can transform to vapor at the slightest warming, begin their escape first, creating the initial fuzzy atmosphere that astronomers detected around 3I Atlas, when it was still beyond the orbit of Jupiter. As the comet draws closer to the Sun, progressively less volatile materials join the exodus, each contributing its own signature to the growing spectacle. What makes this process particularly fascinating is how it mirrors, in slow motion, the rapid disintegration we observe when meteoroids encounter our atmosphere. In both cases, we're witnessing the fundamental inability of matter to maintain its original form when subjected to conditions drastically different from those in which it formed. The meteoroid, compressed and heated to thousands of degrees in mere seconds, undergoes catastrophic structural failure. The comet, gently warmed over months, experiences a more gradual but equally profound transformation as its very substance streams away into space. The dust that accompanies this sublimation tells its own remarkable story. Embedded within the ices of 3I Atlas are countless microscopic particles, silicates, and organic compounds that condense from the stellar winds and supernova remnants that populated the comet's birth region. These dust grains, some no larger than the particles in cigarette smoke, have remained pristine within their icy matrix for billions of years. Now, as the supporting ice sublimates away, they find themselves liberated into space for the first time since their formation. This dust doesn't simply drift away randomly. Instead, it follows the complex choreography dictated by solar radiation pressure and the comet's own gravity, creating the magnificent tail that makes comets such compelling objects of observation. The larger particles, those with enough mass to resist the gentle push of sunlight, tend to follow the comet's orbital path, while the finest dust gets swept into a spectacular curved tail that can stretch for millions of kilometers behind the nucleus. Recent observations have revealed that 3I Atlas is shedding material at a prodigious rate, losing several tons of mass every day as it approaches the Sun. This might seem like a lot, but when distributed across the comet's estimated 33 billion ton mass, it represents only a tiny fraction of the whole. Still, over the course of its passage through our solar system, 3I Atlas will sacrifice a significant portion of its substance to create the spectacular display we're witnessing from Earth. The European Space Agency's fleet of Mars orbiters is preparing to document this transformation from a unique perspective as the comet passes closest to the red planet in early October. From Mars, astronomers will be able to observe the sunward side of 3I Atlas, the hemisphere experiencing the most intense heating and therefore the most dramatic outgassing. This viewpoint, impossible to achieve from Earth due to our relative positions, may reveal jets and active regions on the comet's nucleus that remain invisible to terrestrial observers. The HOPE spacecraft, with its ultraviolet spectrometer, is particularly well positioned to detect the characteristic glow of hydrogen atoms created when water molecules in the comet's atmosphere are broken apart by solar radiation. This process, called photodissociation, occurs throughout the comet's growing atmosphere and creates a vast invisible cloud of hydrogen that extends far beyond the visible coma. Mapping this hydrogen envelope will help scientists understand how efficiently 3IATLAS is converting its ancient ice into the building blocks of space. Meanwhile, the ExoMars Trace Gas Orbiter will focus its attention on detecting more complex molecules in the comet's atmosphere, searching for organic compounds that might provide clues about the chemical processes that operated in the comet's birth system. The presence of such molecules in interstellar space has profound implications for our understanding of how the raw materials for life might be distributed throughout the galaxy. But perhaps the most intriguing observations will come from instruments designed to study the comet's nucleus itself, the solid heart of this interstellar wanderer. As gases and dust stream away from the surface, they gradually expose fresh material that has never before felt the touch of starlight. Each newly revealed layer carries within it the chemical memory of different epochs in the comet's formation, like tree rings that record the changing conditions over cosmic time. The surface of 3IATLAS is almost certainly not uniform. Cometary nuclei typically display a patchwork of active and inactive regions, where local variations in composition, structure, or solar illumination create dramatically different responses to heating. Some areas may be rich in volatile ices that create spectacular jets when warmed, while others might be covered by a layer of dust so thick that it insulates the underlying ice from solar heating, creating temporarily dormant regions that could spring to life as the comet's rotation brings them into direct sunlight. This heterogeneity explains why comets often display sudden changes in brightness, or develop new jets and tails with little warning. The nucleus of 3I Atlas is essentially a three-dimensional puzzle of different materials and structures, each responding to solar heating according to its own particular properties. As the comet continues its approach toward the Sun, we may witness the activation of previously quiet regions or the dramatic evolution of existing active areas. The study of these processes has practical implications beyond pure scientific curiosity. Understanding how ices sublimate and how dust behaves in the vacuum of space is crucial for planning future missions to comets and asteroids. The European Space Agency's Rosetta mission, which spent 2 years studying comet Churyumov-Gerasimenko up close, revealed that cometary activity is far more complex and dynamic than previously imagined, with jets turning on and off according to daily cycles of heating and cooling. 3I Atlas, however, presents challenges that no previous comet mission has faced. Its interstellar origin means that its composition and structure may be fundamentally different from the solar system comets we've studied in detail. The ices within its nucleus formed under the influence of another star's radiation, in a chemical environment that may have been quite unlike the conditions that prevailed in our own solar nebula 4.5 billion years ago. This alien chemistry is already revealing itself in the spectroscopic observations being conducted by the James Webb Space Telescope. The unusual abundance of carbon dioxide relative to water suggests that 3I Atlas formed in a region where temperatures were cold enough for carbon dioxide ice to condense, but perhaps too warm for water ice to be abundant. This points to formation in the outer regions of another star system, possibly around a star cooler than our Sun, where the habitable zone would have been much closer to the stellar surface. The detection of carbonyl sulfide, a compound rarely seen in solar system comets, adds another piece to this puzzle. This molecule typically forms through the interaction of carbon monoxide and hydrogen sulfide under specific temperature and pressure conditions. Its presence in 3IATLAS suggests chemical processes that may have been common in the comet's birth system but are rare in our local galactic neighborhood. As we prepare for 3IATLAS to disappear behind the Sun's glare, astronomers are making the most of every remaining night of observation. The comet will be visible through the end of September, after which it will be lost to ground-based telescopes until it re-emerges in December. This disappearance represents more than just an observational challenge. It marks the beginning of the most critical phase of the comet's journey through our solar system. During its hidden passage behind the Sun, 3I Atlas will experience the most intense heating of its billion-year existence. The solar radiation that reaches the comet at its closest approach will be roughly 5 times stronger than what Earth receives, intense enough to sublimate even relatively stable compounds that have remained frozen throughout the comet's interstellar journey. This could trigger dramatic changes in the comet's appearance and activity level, transforming it from a relatively sedate visitor into a spectacular celestial display. The possibility of witnessing such a transformation has astronomers planning intensive observation campaigns for December, when the comet is expected to reappear. Will 3I Atlas emerge unchanged from its solar encounter? Or will months of intense heating have fundamentally altered its character? The answer lies hidden in the complex interplay between the comet's internal structure and the extreme environment it's about to encounter. This uncertainty reflects our limited understanding of how objects from interstellar space respond to conditions in our solar system. Every previous comet we've studied in detail has been a long-term resident of our cosmic neighborhood, shaped by millions of years of repeated passages near the Sun. 3I Atlas, by contrast, is experiencing solar heating for the first time in its existence, making its behavior inherently unpredictable. The comet's massive size, several times larger than previous interstellar visitors, adds another layer of complexity to the situation. Larger comets have more thermal mass, meaning they heat up more slowly, but also retain that heat for longer periods. The interior of 3I Atlas may remain cold, even as its surface experiences intense heating, creating thermal stresses that could lead to structural changes or even fragmentation events. Some of the most spectacular cometary displays in history have occurred when large comets underwent sudden fragmentation near the Sun. Comet West in 1976 split into multiple pieces during its solar passage, creating a magnificent multi-tailed display that was visible even in daylight. More recently, Comet ISON in 2013 appeared to disintegrate completely during its closest approach to the Sun, though some debate remains about whether any substantial fragments survived the encounter. The possibility that 3IA TLAS might undergo similar fragmentation adds an element of suspense to its upcoming solar passage. If the comet does break apart, the resulting debris cloud could create one of the most spectacular celestial displays in recent history. Multiple bright fragments, each developing its own tail and coma, would provide unprecedented opportunities for comparative study of interstellar materials under identical heating conditions. Even if 3I Atlas survives its solar encounter intact, it will likely emerge significantly changed from its pre-passage state. The intense heating will have penetrated deep into its nucleus, potentially altering the distribution of volatile compounds and creating new pathways for gas and dust to escape. The comet that reappears in December may display entirely new jets, tails, and activity patterns that reveal previously hidden aspects of its internal structure. This transformation process offers a unique window into the fundamental physics of matter under extreme conditions. The same principles that govern the explosive disintegration of meteoroids in our atmosphere operate on cometary nuclei, but at a pace that allows us to observe and study each stage of the process. We're essentially watching a controlled experiment in matter transformation, conducted on a scale and under conditions impossible to reproduce in any terrestrial laboratory. The data being collected during this phase of 3IA TLAS's journey will inform our understanding of cometary physics for decades to come. Every measurement of gas production rates, dust emission patterns, and chemical composition provides crucial constraints on theoretical models of how these ancient objects respond to solar heating. The insights gained from studying this interstellar visitor will undoubtedly influence the design of future comet missions and deepen our understanding of the role these objects play in the cosmic cycle of matter and energy. As we await the comet's reappearance in December, we're reminded that disappearance and transformation are fundamental themes in astronomy. Stars are born, shine for billions of years, and then fade or explode, scattering their material to begin the cycle anew. Comets emerge from the outer darkness, approach the warmth of stars, and then retreat again, carrying with them the memory of their brief illumination. Showers participate in this same eternal dance, arriving from the meteoroids that create our nightly meteor, the cold depths of space to meet their end in brilliant flashes that briefly outshine the stars themselves. Their disintegration is not truly an ending, but a transformation, releasing energy and returning material to the cosmic cycle that will eventually build new worlds and perhaps new forms of life. In this grand cosmic context, 3IATLAS represents something extraordinary, a messenger from another star system, carrying within its ancient nucleus the chemical memory of processes that occurred billions of years ago, under conditions we can barely imagine. Its journey through our solar system offers us a rare glimpse into the diversity of materials and conditions that exist throughout our galaxy, expanding our understanding of planetary formation processes and the chemical evolution of stellar systems. As the comet prepares for its transformation behind the Sun, we can only wait and wonder what changes this ancient wanderer will undergo in the intense radiation environment near our star. Will it emerge as a changed visitor, its surface scarred and altered by unprecedented heating? Or will its deep interior finally be awakened, creating new displays of activity that reveal secrets hidden for billions of years? The answer to these questions lies just months away, hidden behind the overwhelming brightness of our star. But the waiting itself is part of the wonder. A reminder that the universe still holds mysteries that unfold on timescales both vast and intimate, connecting us to processes that began long before our planet existed and will continue long after our sun has faded to a dim ember in the cosmic dark. The study of meteoroid disintegration has revealed something rather curious about the nature of fragmentation itself. When researchers first began modeling these high-speed atmospheric encounters, they assumed the process would be relatively straightforward. Heating would weaken the material, pressure would build up, and eventually the object would break apart in a predictable manner. But reality, as it so often does, proved far more intricate and beautiful than these early models suggested. What scientists discovered is that meteoroid fragmentation follows patterns reminiscent of natural phenomena we observe here on Earth, from the way lightning branches through storm clouds to how cracks propagate through breaking glass. The disintegration doesn't happen uniformly across the meteoroid's surface. Instead, it begins at points of weakness, tiny flaws or variations in density that become focal points for the tremendous forces at work. From these initial failure points, fractures spread outward in complex branching patterns, creating a cascade of destruction that can reduce a house-sized boulder to dust in mere seconds. This fracturing process operates according to principles that physicists call scaling laws, mathematical relationships that describe how certain phenomena behave as size changes. The same equations that predict how a wine glass will shatter when dropped also govern in modified form how a meteoroid fragments during atmospheric entry. It's a testament to the underlying unity of physics that the same fundamental principles operate whether we're talking about something as delicate as crystal stemware or as dramatic as cosmic bombardment. The temperature gradients that develop within a meteoroid during atmospheric entry create their own fascinating dynamics. The outer surface, directly exposed to the compressed air's tremendous heat, can reach temperatures that would vaporize steel. Meanwhile, just centimeters beneath this molten exterior, the material might remain at the frigid temperatures of deep space. This extreme temperature difference sets up thermal stresses that can literally tear the object apart from within, much like how a glass tumbler cracks when you pour hot water into it on a cold morning. But there's another player in this cosmic drama that often goes unnoticed: time itself. The entire process of meteoroid disintegration, from initial atmospheric contact to final fragmentation, typically unfolds in less than 10 seconds. For comparison, it takes longer to sneeze than it does for a meteoroid the size of a small car to be completely destroyed by our atmosphere. This extraordinarily compressed timeline means that many of the physical processes we might observe in a laboratory setting simply don't have time to occur. Instead, the meteoroid experiences what researchers call non-equilibrium conditions, where different parts of the system haven't had time to reach a steady state. This temporal compression creates some wonderfully counterintuitive effects. A meteoroid's interior might still be frozen solid even as its surface is hot enough to emit visible light. The pressure waves generated by atmospheric compression might not have time to propagate through the entire object before fragmentation begins. These non-equilibrium conditions make meteoroid behavior notoriously difficult to predict, which is why atmospheric entry remains an active area of research despite decades of study. The debris cloud that results from meteoroid fragmentation has its own remarkable properties. Rather than simply dispersing randomly, the fragments tend to maintain a coherent structure as they continue their descent through the atmosphere. Researchers have observed that the debris cloud often takes on a distinctive shape, elongated in the direction of travel and gradually expanding as atmospheric drag affects different-sized fragments in different ways. The largest pieces, with their greater momentum, tend to penetrate deeper into the atmosphere, while the smallest fragments are quickly decelerated and dispersed. This creates what astronomers call a meteor train, a glowing trail of ionized gas and microscopic debris that can persist for several minutes after the original meteoroid has been completely destroyed. These trains are visible to radar systems long after the visual meteor has faded, allowing scientists to track the final fate of the disintegrated material as it settles into the upper atmosphere. Some of this material eventually makes its way to the ground as microscopic spherules, tiny droplets of once molten rock that can be collected and analyzed to learn about the original meteoroid's composition. The connection between these terrestrial fireworks and our interstellar visitor becomes clearer when we consider the role that structure plays in determining an object's fate. 3. Atlas, with its complex mixture of ices and embedded dust, represents a fundamentally different type of material than the rocky or metallic meteoroids that typically create meteor displays. Where a stony meteoroid might fragment catastrophically under atmospheric stress, a comet nucleus responds more gradually to heating, allowing us to observe the transformation process in exquisite detail. The nucleus of 3I Atlas is likely what planetary scientists call a rubble pile, a loosely bound collection of smaller pieces held together by weak gravitational attraction and the frozen matrix of various ices. This structure, common among comets, makes them remarkably fragile objects despite their often impressive size. The gentle gravitational forces that bind the pieces together are easily overwhelmed by the thermal stresses and gas pressure generated by solar heating, which is why comets occasionally split apart spontaneously, even without any external disturbance. The famous case of Comet Shoemaker-Levy 9, which fragmented into more than 20 pieces before colliding with Jupiter in 1994, demonstrates just how fragile these cosmic snowballs can be. The comet's encounter with Jupiter's powerful gravitational field was enough to overcome the weak forces holding its nucleus together, stretching it into a chain of fragments that astronomers dubbed the String of Pearls. Each fragment that eventually impacted Jupiter created an explosion visible from Earth, collectively releasing energy equivalent to millions of hydrogen bombs. 3. Atlas, fortunately, faces no such dramatic fate during its passage through our solar system. Its trajectory will carry it safely past all the major planets, though it will experience gravitational tugs from Jupiter and Saturn that will slightly modify its path through space. These gravitational encounters, while not strong enough to fragment the comet, will impart small changes to its velocity that will affect its ultimate trajectory as it leaves our solar system and returns to interstellar space. The comet's encounter with our sun's radiation, however, presents a different kind of challenge altogether. Unlike the gravitational stresses that tore apart Shoemaker-Levy 9, solar heating works from the outside in, gradually warming the comet's surface and penetrating into its interior. This creates a complex three-dimensional temperature distribution within the nucleus, with hotspots corresponding to areas of direct solar illumination and cooler regions in shadows cast by the irregular topography of the comet's surface. Recent computer models of cometary heating suggest that 3IA-TLAS may develop what researchers call thermal waves, regions of elevated temperature that propagate slowly into the comet's interior as solar heating continues. These thermal waves can trigger sublimation events deep within the nucleus, creating pockets of gas pressure that must find pathways to escape to the surface. The result can be sudden jets of gas and dust that appear with little warning, creating new features in the comet's coma and tail. The timing of such outbursts is notoriously difficult to predict because it depends on the detailed internal structure of the comet, information that remains largely hidden from our instruments. We can observe the surface and the material streaming away from it, but the interior remains a mystery wrapped in ancient ice. This uncertainty is part of what makes cometary astronomy so exciting and unpredictable. Even experienced observers are regularly surprised by sudden changes in cometary behavior that reveal new aspects of these complex objects. The Hubble Space Telescope's ongoing monitoring of 3IA-TLAS has already revealed subtle changes in the comet's appearance as it continues its approach toward the Sun. The dust coma surrounding the nucleus has grown noticeably larger and brighter over the past several weeks, indicating that the rate of material loss is increasing as solar heating intensifies. Spectroscopic analysis shows that the composition of the coma is also evolving, with different molecular species becoming more or less prominent as various ices respond to the changing temperature conditions. This evolutionary process mirrors, in many ways, the life cycle of stars themselves. Just as a star burns through different types of nuclear fuel as it ages, creating heavier and heavier elements in its core, a comet consumes its most volatile materials first, gradually exposing less reactive compounds as its journey continues. The analogy isn't perfect, of course, but it illustrates how astronomical objects undergo systematic changes as they respond to their environment. The dust being expelled from 3I Atlas carries within its microscopic grains a record of the conditions that existed in the comet's birth system billions of years ago. These particles, no larger than cigarette smoke, contain isotopic ratios and mineral compositions that reflect the stellar environment where they first condensed from hot gas. By analyzing this dust, scientists can essentially perform archaeology on another star system, reconstructing the history of stellar evolution and planetary formation processes that occurred long before our own sun ignited. The challenge lies in capturing and analyzing these infinitesimal messengers from another world. Even the most sensitive instruments struggle to detect individual dust grains against the overwhelming background of solar system material that fills interplanetary space. It's rather like trying to identify a specific raindrop in a thunderstorm while blindfolded and wearing mittens. The task requires not just sophisticated technology, but also careful statistical analysis to separate the signal from the noise. Some of the most promising approaches involve studying the comet's tail itself, where the dust grains are concentrated and moving in predictable patterns. As 3. I-Atlas continues to approach the Sun. Its tail is becoming increasingly prominent, stretching across several degrees of sky as seen from Earth. This tail isn't just a beautiful astronomical sight. It's a natural laboratory where interstellar dust interacts with solar radiation in ways that reveal information about the particle's size, composition, and structure. The way sunlight scatters off these dust grains creates subtle color variations along the length of the tail, with different wavelengths of light being affected differently depending on the size and shape of the particles. By carefully measuring these color variations, astronomers can infer properties of the dust that would be impossible to determine through direct sampling. It's a technique that turns the entire solar system into a giant laboratory instrument, using the sun itself as a light source for studying matter from another star. The European Southern Observatory's Very Large Telescope in Chile has been particularly successful in these observations, using its advanced spectroscopic capabilities to dissect the light from 3IATLAS's tail into its component wavelengths. Each molecular species in the comet's atmosphere absorbs and emits light at characteristic frequencies, creating a spectral fingerprint that reveals not just what compounds are present, but also their relative abundances and physical conditions. These observations have confirmed the presence of several molecules that are rare in solar system comets, including complex organic compounds that may have formed through radiation processing in the interstellar medium. The discovery of these molecules raises intriguing questions about the role that interstellar chemistry plays in creating the building blocks of life. If such compounds are common in comets from other star systems, it suggests that the raw materials for biology might be widely distributed throughout the galaxy. The implications extend far beyond our understanding of 3IATLAS itself. Every interstellar object that visits our solar system provides a sample of conditions elsewhere in the galaxy, offering insights into stellar evolution, planetary formation, and the chemical processes that operate in different cosmic environments. In essence, these visitors serve as natural space probes, carrying information across distances that would take our fastest spacecraft millions of years to traverse. The rarity of interstellar visitors makes each one precious beyond measure. Current estimates suggest that objects like 3I Atlas pass through the inner solar system only once every few years, and most are discovered too late for detailed study. The early detection of 3IATLAS has provided an unprecedented opportunity to monitor an interstellar object throughout its entire passage, from its initial approach through its closest solar encounter and eventual departure back into the cosmic deep. This comprehensive observation campaign involves not just ground-based telescopes, but also space-based instruments positioned throughout the solar system. The coordination required to synchronize observations across multiple platforms and wavelengths represents a remarkable achievement in international scientific cooperation. Astronomers from dozens of countries are contributing data and expertise to ensure that no detail of 3IATLAS's passage goes unrecorded. The James Webb Space Telescope, with its unparalleled sensitivity to infrared radiation, has been particularly valuable for studying the comet's thermal emission. Unlike visible light observations that show us reflected sunlight, infrared measurements reveal the actual temperature of the comet's surface and the thermal properties of the dust in its coma. This information is crucial for understanding how efficiently 3IATLAS converts solar energy into the kinetic energy of escaping gas and dust. Webb's observations have revealed that the comet's nucleus has a surprisingly low thermal inertia, meaning it heats up and cools down quickly as it rotates, and different areas come into or go out of sunlight. This suggests a surface covered by fine dust, or possibly a fluffy, porous structure that doesn't conduct heat well into the interior. Such properties are consistent with the comet being a pristine remnant from the early days of its birth system, largely unchanged by the weathering processes that have modified objects in our own solar system over billions of years. The rotation of 3IATLAS itself tells its own story about the comet's history and internal structure. Precise measurements of how the comet's brightness varies as it spins reveal that it completes one rotation approximately every 14 hours, a relatively rapid spin for such a large object. This rotation rate, combined with the comet's elongated shape inferred from brightness variations, suggests that 3IATLAS may have been spun up by asymmetric outgassing during previous encounters with other stars during its long journey through the galaxy. The dynamics of rotating comets under the influence of asymmetric gas jets create what planetary scientists call non-gravitational forces, gentle but persistent pushes that can significantly alter an object's trajectory and rotation over long periods. For 3I Atlas, these forces during its current passage near our Sun may be changing its rotation rate and orientation in space, effects that will propagate forward to influence its future journey through the cosmos. As the comet continues its approach toward its October rendezvous with the Sun, these rotational effects are becoming increasingly important. The changing orientation of the nucleus relative to the Sun's direction creates daily cycles of heating and cooling that drive complex patterns of gas and dust emission. Understanding these cycles requires careful timing of observations to capture the comet at different rotational phases, building up a complete picture of how activity varies across the nucleus surface. Ground-based observers have noted that 3I Atlas displays a clear periodicity in its brightness, waxing and waning with its 14-hour rotation period. But superimposed on this regular cycle are more subtle variations that suggest the presence of discrete active regions on the comet's surface, areas where concentrations of volatile ices create enhanced outgassing when illuminated by the Sun. Mapping these active regions provides insight into the internal structure and composition of the nucleus, revealing how billions of years of interstellar travel have shaped this ancient visitor. The discovery that 3I Atlas has distinct active regions rather than uniform surface activity suggests a complex internal structure, possibly layered like an onion with different compositions at different depths. As solar heating penetrates deeper into the nucleus, it may activate previously dormant regions, creating new jets and changing the overall character of the comet's display. This evolutionary process will continue throughout the comet's passage, potentially creating dramatic changes in its appearance that reflect the awakening of its most deeply buried ices. The anticipation surrounding these potential changes has astronomers around the world preparing for an intensive observation campaign during the comet's closest approach to the Sun. Although 3I Atlas will be hidden behind solar glare during this critical period, spacecraft positioned throughout the solar system will maintain their vigil, ready to document any outbursts or dramatic changes that occur during the comet's most intense heating phase. The possibility that 3I Atlas might undergo spectacular fragmentation or outburst events during its hidden passage adds an element of cosmic suspense to its story. When it re-emerges from behind the Sun in December, will it appear as the same stately visitor we've been observing? Or will months of intense solar heating have transformed it into something altogether more dramatic and unpredictable? The answer lies hidden in the delicate balance between the comet's internal structure and the extreme conditions it's about to encounter, a balance that has remained undisturbed for billions of years, but is now about to be tested by the full fury of our Sun's radiation. Whatever happens during those hidden months, 3I Atlas will emerge forever changed, carrying with it the scars and stories of its brief but intense encounter with the heart of our solar system. The story becomes even more captivating when we consider that the very concept of thermal equilibrium, something we take for granted in our earthly experience, becomes meaningless in the extreme conditions of space. Here on our planet, when you place a hot object next to a cold one, heat flows naturally from warm to cool until both reach the same temperature. It's a fundamental principle that governs everything from brewing tea to designing heating systems. But 3I Atlas exists in an environment where such simple rules break down completely. In the vacuum of space, heat can only transfer through radiation, that invisible dance of electromagnetic waves that carries energy across the cosmic void. There's no air to conduct warmth, no medium through which temperature can equalize in the familiar ways we understand. This means that one side of the comet's nucleus, facing the Sun, might be hot enough to sublimate water ice, while the opposite side remains locked at temperatures barely above absolute zero. It's as if the comet exists in multiple thermal worlds simultaneously, each responding to completely different physical conditions. This thermal schizophrenia creates some wonderfully peculiar effects. Imagine walking around 3IATLAS with a magical thermometer that could measure temperature through its nucleus. You might start on the sunward side where the surface is warm enough to melt lead. Then walk just a few meters toward the shadowed regions where your breath would freeze instantly if such a thing were possible in vacuum. The temperature gradient would be so steep that you could literally have one foot in summer and the other in the depths of interstellar winter. But it's not just temperature that varies so dramatically across the comet's surface. The rate at which different ices sublimate depends not only on temperature, but also on the local pressure conditions and the presence of dust that might insulate underlying volatile materials. Areas rich in water ice might remain relatively quiet until solar heating penetrates deep enough to reach them, while regions containing more exotic compounds could spring to life with vigorous outgassing at much greater distances from the sun. This creates a kind of geological awakening as 3IATLAS approaches its solar encounter. Different layers within the nucleus respond to heating at different rates, like a complex musical instrument where each string vibrates at its own frequency. The result is a symphony of sublimation, with various chemical species joining and leaving the comet's growing atmosphere according to their own thermal rhythms. The dust that gets carried away by these sublimating gases tells its own fascinating story about the comet's internal architecture. Unlike the uniform particles you might expect from a homogeneous object, the dust from 3IATLAS displays a remarkable diversity of sizes, shapes, and compositions. Some grains are microscopic crystalline structures that formed in the stellar winds of dying stars, while others are fluffy aggregates of organic compounds that may have been assembled through gentle collisions in the interstellar medium. This diversity reflects the complex history of how cometary nuclei form and evolve. Rather than condensing from a single uniform cloud of material, comets like 3IATLAS are thought to be gravitational accumulations of countless smaller pieces, each with its own unique origin story. Some components might have condensed directly from the gas around the comet's birth star, while others could be recycled material from even older stellar generations, creating a kind of cosmic archaeology preserved in ice. The process of thermal processing that occurs as 3I Atlas approaches our Sun gradually reveals these hidden layers of history. As the outermost material sublimates away, it exposes progressively older and more primitive components that have been shielded from space weathering throughout the comet's billion-year journey. In effect, we're witnessing the slow unpacking of a time capsule that has been sealed since the era when our own solar system was nothing more than a collapsing cloud of gas and dust. The spectroscopic signatures detected by the James Webb Space Telescope have already revealed evidence of this layered structure. Early observations showed relatively simple compounds dominated by carbon dioxide and water vapor. But as the comet's activity has increased, more complex molecules have begun appearing in its atmosphere. These newer arrivals likely originate from deeper within the nucleus, regions that are only now beginning to feel the effects of solar heating. The emergence of these deeper materials creates what astronomers call compositional evolution, a gradual change in the chemical makeup of the comet's atmosphere that reflects the internal structure of its nucleus. It's rather like watching an onion being peeled in slow motion, with each layer revealing slightly different ingredients that tell us about the conditions under which that particular region formed. This evolutionary process operates on timescales that bridge the gap between the instantaneous destruction of meteoroids and the geological patience of planetary formation. Where meteoroid disintegration happens in seconds and mountain building takes millions of years, cometary evolution unfolds over months and years, making it possible for human observers to follow the entire process from beginning to end. The connection between these different timescales reveals something profound about how the universe organizes itself across different scales of space and time. The same physical principles that govern the behavior of atoms in a laboratory also control the dynamics of comets, planets, and stars. But the manifestations of these principles depend entirely on the context in which they operate. A pressure wave that might shatter a meteoroid in our atmosphere becomes a gentle thermal pulse that slowly awakens ancient ices in a comet's nucleus. This universality of physical law is one of the most beautiful aspects of studying celestial mechanics. Whether we're examining the disintegration of space debris over our heads or the gradual transformation of an interstellar visitor millions of kilometers away, we're observing different expressions of the same fundamental processes. The equations that describe fluid flow, heat transfer, and material strength apply equally well to both situations, adjusted only for the different scales and conditions involved. The mathematical elegance of these relationships has practical implications for understanding and predicting the behavior of objects throughout the solar system. The same computational models used to study meteoroid fragmentation can be adapted to predict how cometary nuclei respond to solar heating, while observations of cometary outgassing provide insights into the material properties of asteroids and other small bodies. But perhaps most remarkably, these connections extend beyond our own solar system to encompass the behavior of matter throughout the universe. The principles governing 3IATLAS's transformation apply equally to comets orbiting other stars, to the formation of planetary systems in distant galaxies, and to the evolution of matter in environments we can barely imagine. In studying our interstellar visitor, we're not just learning about one particular object, but gaining insights into processes that operate wherever matter encounters energy under extreme conditions. The philosophical implications of this universality are profound. Every streak of light we see during a meteor shower connects us to the same physical processes that are slowly transforming 3IATLAS as it approaches our Sun. Every observation of our interstellar visitor reveals principles that govern the behavior of matter throughout the cosmos. We're not separate observers watching distant events unfold, but participants in a vast interconnected system where the same rules apply from the smallest scales to the largest. This interconnectedness becomes especially apparent when we consider the role that time plays in these various processes. The meteoroid that creates a brilliant fireball experiences its entire atmospheric encounter in a few brief seconds, while 3IATLAS has been traveling toward this moment for hundreds of millions of years. Yet both objects are governed by the same physics, operating on different temporal scales, but following identical fundamental principles. The comet's long journey through interstellar space represents a kind of cosmic patience that challenges our human perception of time. While we measure our lives in decades and our civilizations in millennia, 3I Atlas has been drifting through the galaxy since long before complex life appeared on Earth. Its nucleus contains ices that froze when the universe was young, preserving within their crystalline structure the chemical conditions that existed in a stellar system that may have died billions of years ago. Now, in the final months of its passage through our solar system, all that ancient history is being written across the sky in jets of gas and streams of dust. The transformation we're witnessing represents not just the awakening of dormant ices, but the culmination of an epic journey that began in the depths of space and time. Every molecule that escapes from the comet's nucleus carries with it information about conditions that existed when the galaxy itself was young and different. The James Webb Space Telescope's ability to analyze this escaping material in unprecedented detail means that we're essentially reading the autobiography of another star system, written in the language of atoms and molecules. The isotopic ratios of different elements reveal the nuclear processes that operated in the comet's birth star, while the presence of complex organic compounds hints at the chemical pathways that may have operated in that distant environment. This chemical archaeology extends our understanding far beyond the boundaries of our own solar system, providing direct evidence of how matter behaves under stellar conditions, different from those that shaped our own cosmic neighborhood. Every measurement of 3IATLAS's composition expands our knowledge of stellar evolution, planetary formation, and the chemical processes that govern the universe at large. The European Space Agency's coordinated observation campaign, involving multiple spacecraft positioned throughout the solar system, represents an unprecedented effort to document these processes in real time. Never before have we had the technological capability to monitor an interstellar object so comprehensively from so many different vantage points using such a diverse array of instruments. The data streaming back from these various missions is creating the most complete picture ever assembled of how an object from another star system responds to conditions in our own. Every temperature measurement, every spectroscopic analysis, every image of the comet's evolving structure adds another piece to a puzzle that connects our local cosmic environment to the broader galactic community of stellar systems. As 3. Atlas continues its approach toward its October appointment with the Sun, the intensity of these observations is increasing. Ground-based telescopes are capturing images and spectra on a nightly basis, documenting subtle changes in the comet's appearance that reflect the ongoing transformation of its nucleus. Space-based instruments are monitoring the comet continuously, alert for any sudden changes that might indicate dramatic internal restructuring. The anticipation surrounding the comet's closest approach to the Sun has created something of a countdown atmosphere in the astronomical community. Researchers are preparing for the possibility that 3IATLAS might undergo one of the spectacular outburst events that occasionally transform comets from sedate visitors into dramatic celestial displays. Such events, while unpredictable, often occur when internal stresses from heating overcome the structural integrity of the nucleus. The famous brightening of Comet Holmes in 2007 provides a dramatic example of how quickly such transformations can occur. That comet increased in brightness by a factor of 1 million in less than 2 days, creating a spectacular naked-eye object where none had been visible before. The cause of such outbursts remains poorly understood, but they appear to involve the sudden release of large amounts of gas and dust from previously inactive regions of the nucleus. If 3I Atlas were to undergo a similar outburst during its hidden passage behind the Sun, the first signs might not become apparent until the comet re-emerges in December. The possibility of such a dramatic transformation adds an element of cosmic suspense to the comet's story, reminding us that even our most sophisticated models and predictions cannot fully capture the complex behavior of these ancient visitors. The uncertainty surrounding the comet's behavior during its solar encounter reflects our limited understanding of how matter responds to extreme conditions over cosmic timescales. While we can predict the general effects of solar heating on cometary ices, the detailed behavior depends on internal structures and compositions that remain largely hidden from our instruments. Each comet is unique, shaped by its own particular history and internal architecture. 3. Atlas, with its interstellar origin and pristine composition, represents an especially challenging case for theoretical models. Unlike solar system comets that have undergone multiple heating cycles during repeated passages near the Sun, our interstellar visitor is experiencing intense solar radiation for the first time in its existence. The response of its ancient ices to this unprecedented heating cannot be predicted with certainty from observations of other comets. This uncertainty is part of what makes cometary astronomy so fascinating and unpredictable. Even experienced researchers are regularly surprised by sudden changes in cometary behavior that reveal new aspects of these complex objects. The interplay between structure, composition, and thermal evolution creates a system so intricate that small changes in initial conditions can lead to dramatically different outcomes. The mathematical concept of sensitive dependence on initial conditions, sometimes called the butterfly effect, applies beautifully to cometary dynamics. A small variation in internal structure or composition might determine whether 3IATLAS emerges from its solar encounter as a quiet, well-behaved visitor, or transforms into a spectacular multi-tailed display that graces our skies for months to come. This sensitivity to initial conditions connects cometary behavior to some of the most profound questions in physics and astronomy. How do complex systems evolve over time? What role does chance play in determining the outcomes of physical processes? How do we make predictions about systems that are inherently unpredictable beyond certain timescales? These questions extend far beyond the study of individual comets to encompass our understanding of planetary formation, stellar evolution, and the development of structure throughout the universe. The same principles that make 3IATLAS's behavior unpredictable also govern the formation of galaxies, the evolution of planetary atmospheres, and the emergence of life itself. In this broader context, our interstellar visitor serves as more than just an object of scientific study. 3I Atlas becomes a window into the fundamental nature of change and transformation in the universe, a cosmic laboratory where we can observe the interplay between order and chaos, predictability and surprise, ancient history and present transformation. As the comet prepares for its disappearance behind the sun, we're reminded that some of the most profound changes in the universe occur not in dramatic explosions or catastrophic collisions, but in the quiet, patient processes of heating, sublimation, and gradual transformation. The same gentle persistence that carved the Grand Canyon and shaped the continents is now slowly awakening. 3IATLAS from its billion-year slumber, releasing into space the chemical memories of another star. The story of disappearing meteoroids reveals something rather enchanting about the relationship between size and survival in our cosmic neighborhood. You see, there exists what scientists have dubbed the Goldilocks zone of destruction, though not the familiar one we associate with planetary habitability. This particular zone describes the range of sizes where incoming space rocks face the most dramatic fate when encountering our atmosphere. Objects smaller than a grain of sand drift down through our air like cosmic snow, their tiny mass insufficient to generate the catastrophic heating that destroys their larger cousins. Meanwhile, truly massive asteroids, those rare giants measuring kilometers across, possess enough thermal mass and structural integrity to punch through our atmospheric shield, though thankfully such encounters occur only once every few million years. It's the objects caught in between, from pebbles to boulders, that face the most spectacular destruction. This size-dependent survival creates fascinating patterns in what reaches our planet's surface. The meteorite collections housed in museums around the world represent a highly biased sample of cosmic debris, consisting almost entirely of either the tiniest particles or fragments from the most massive impacts. The middle ground, that vast range of sizes that creates our most beautiful meteor showers, rarely survives the journey intact. The physics underlying this selective destruction involves what researchers call aerodynamic loading, the tremendous stress placed on an object as it compresses the air in front of it at hypersonic speeds. A grain of sand experiences negligible loading because its small size means it interacts with only a tiny volume of air. A mountain-sized asteroid, while experiencing enormous total forces, has sufficient structural mass to absorb that stress without catastrophic failure. But objects of intermediate size face forces that perfectly match their structural limitations, leading to spectacular fragmentation. This principle operates throughout nature, from the way waves break on shorelines to how avalanches cascade down mountainsides. There's always a characteristic scale at which competing forces balance in ways that produce the most dramatic effects. For meteoroids entering Earth's atmosphere, that scale happens to coincide with sizes ranging from marbles to automobiles, which explains why these objects create such magnificent displays, while smaller and larger visitors pass through more quietly. The dust trails left behind by fragmenting meteoroids create their own subtle beauty in the upper atmosphere. Long after the visible meteor has faded, microscopic particles continue to drift downward, their surfaces bearing the scars of their violent birth in the compressed air of atmospheric entry. These particles, when examined under powerful microscopes, reveal textures and compositions that tell stories of extreme heating and rapid cooling. processes that occurred in mere milliseconds, but left permanent signatures in the material. Some of these cosmic dust grains eventually find their way into ice cores drilled from glaciers and polar ice sheets, where they become part of Earth's geological record. Scientists studying these ancient layers can identify periods of increased meteoric activity, times when our planet passed through particularly dense streams of interplanetary debris. It's a reminder that the spectacular light shows we observe overhead have been occurring for billions of years, long before there were eyes to appreciate their beauty. The seasonal meteor showers that grace our night skies throughout the year represent the most predictable manifestation of this cosmic recycling process. Each annual display corresponds to Earth's passage through the debris trail of an ancient comet, material that was expelled during previous approaches to the Sun and now spreads in a vast elliptical cloud around the comet's orbit. When our planet intersects these streams, we witness the delayed disintegration of material that might have left its parent comet centuries or millennia ago. The Perseid meteor shower of mid-August, perhaps the most reliable and spectacular of these annual displays, originates from Comet Swift-Tuttle, which last passed through the inner solar system in 1992. The meteors we see each August are the remnants of material expelled during that passage, and many previous ones, particles that have been slowly spreading along the comet's orbital path for decades. Each streak of light represents the final moment of a cosmic wanderer that began its journey when your grandparents might have been children. This temporal disconnect between cause and effect adds a poetic dimension to meteor watching. The light you see tonight might originate from dust expelled when the comet was last active during the Renaissance, or perhaps during the age of dinosaurs. Time becomes fluid when contemplating these connections, as the immediate spectacle of atmospheric incineration links us to events that occurred across vast spans of history. The connection between meteor showers and their parent comets also illuminates the gradual evolution of these cosmic objects over time. Each passage near the Sun strips away a layer of material from a comet's nucleus, slowly reducing its mass and changing its composition. Eventually, after millions of years and countless solar encounters, the comet exhausts its supply of volatile materials and becomes a dormant, rocky remnant, indistinguishable from the asteroids that populate the inner solar system. This evolutionary process means that the meteor showers we enjoy today represent a temporary phenomenon in cosmic terms. Displays are gradually the debris streams that create these dispersed by planetary gravitational influences and the subtle pressure of solar radiation. New showers appear as fresh comets enter the inner solar system for the first time, while older displays slowly fade as their parent streams become too dispersed to create concentrated activity. 3I Atlas, during its current passage through our solar system, is actively contributing to this ongoing process of cosmic distribution. The dust streaming away from its nucleus will continue to orbit the Sun long after the comet itself has departed for interstellar space. Some of this material may eventually encounter Earth's atmosphere, creating brief flashes of light that carry within them the chemical fingerprints of another stellar system. The possibility that future meteor observers might witness the incineration of truly interstellar dust adds an extra layer of significance to 3I Atlas's passage. Unlike the familiar debris from solar system comets, these particles would represent samples of material that formed under entirely different stellar conditions, offering glimpses of chemistry and physics operating in distant corners of the galaxy. The process by which this interstellar material might eventually reach our atmosphere involves the same complex gravitational choreography that shapes all orbital mechanics in the solar system. The dust expelled from 3I Atlas will initially follow trajectories similar to the comet's own path, but over time, perturbations from planetary gravity and radiation pressure will gradually alter these orbits. Some particles might be ejected from the solar system entirely, while others could be nudged into paths that eventually intersect Earth's orbit. The timescales involved in this process stretch far beyond human experience. The interstellar dust we might observe as meteors centuries from now is being created today by three IATLAS's ongoing transformation. Future generations of astronomers might witness displays that we can only imagine, meteors that carry within their brief existence the story of our current interstellar visitor. This forward projection of cause and effect mirrors the backward connections we observe in existing meteor showers. Just as tonight's Perseids originated from material expelled by Swift-Tuttle decades ago, the interstellar meteors of the future are being born today in the warming nucleus of 3I Atlas. The universe operates on these vast temporal scales, where actions of time that dwarf human civilization. The study of meteor shower evolution provides insights into how and consequences are separated by spans debris streams disperse and evolve over cosmic time. Computer simulations can track individual particles for thousands of years into the future, predicting how gravitational encounters with planets diffuse clouds. These models reveal gradually spread initially compact streams into broad, that meteor showers have natural lifetimes, beginning as narrow streams that create intense but brief annual displays, then gradually broadening and weakening until they merge into the background of sporadic meteoric activity. The quadrantid meteor shower of early January provides an excellent example of this evolutionary process. This display produces some of the most intense meteoric activity of the year, with peak rates occasionally exceeding 100 meteors per hour. However, the shower's activity is extremely brief, lasting only a few hours compared to the weeks-long activity periods of other major displays. This brevity suggests that the quadrantids represent a relatively young debris stream that has not yet had time to disperse significantly along its orbit. Conversely, some of the weaker annual showers may represent the aged remnants of once spectacular displays, their parent streams now so dispersed that only their passage. The torrid meteor shower complex, a gentle enhancement in meteoric activity, marks to represent such an evolved system, where the original, associated with comet Encke, appears debris stream, has fragmented into multiple components that create several distinct periods of enhanced activity throughout the autumn, a framework for understanding how 3IATLAS's contribution months. These observations of shower evolution provide to future meteoric displays might unfold. Initially, any particles that eventually encounter Earth will likely arrive in concentrated bursts, creating brief but potentially intense displays. Over time, gravitational perturbations will spread this material into broader streams, creating longer duration but less intense activity periods. The chemical eye atlas should be distinctly different from those composition of meteors derived from three originating in our solar system, potentially allowing future observers to identify them even centuries after the comet's departure. The unusual isotopic ratios and exotic mission from another star system delivered free compounds detected in the comet's currentors with confirmed interstellar origins represents and marking any future meteors as definitely interstellar in activity could serve as fingerprints, origin. The prospect of witnessing MEET would provide natural experiments in comparative stellar chemistry, allowing researchers exciting possibility for future astronomy. Such events. Each interstellar meteor would be a microscopic sample return to study how different stellar environments produce different types of materials of charge by the natural dynamics, even as we anticipate these future possibilities. The immediate spectacle of 3IATLAS continues of galactic motion, but to unfold with each passing night. Ground-based observers report that the comet is the background stars. The transformation that comet has began billions of years ago in the coal with the sun, its tail growing longer and more prominent against steadily brightening as it approaches its October encounter, aiming toward Space Agency's Mars depths of interstellar space, is now accelerating regular observations of its climax. The European Express orbiter has been conducting it, prepares for its close approach to the red planet in early October. These observations will provide a unique perspective on 3IATLAS's sunward hemisphere, the side experiencing the most intense heating and therefore the most dramatic activity. The view from Mars will reveal details invisible to Earth-based observers, potentially showing jets and active regions that face away from our planet. The coordination required to maximize the scientific return from 3IATLAS's passage involves telescopes and spacecraft positioned throughout the solar system, each contributing its own unique perspective to the comprehensive portrait being assembled. The Hubble Space Telescope continues its monitoring of the comet's overall structure and activity, while the James Webb Space Telescope focuses on the detailed chemistry of the gases streaming away from the nucleus. This multi-platform approach represents a revolution in how astronomers study transient phenomena. Rather than relying on single observations from individual instruments, modern campaigns can combine data from dozens of sources to create detailed, multidimensional pictures of evolving systems. The result is an understanding of cometary behavior that would have been impossible just a few decades ago. The technological capabilities that make such comprehensive studies possible also highlight how much our understanding of meteoroid disintegration has advanced. Early observers could only document the visual appearance of meteors and estimate their brightness and duration. Modern instruments can analyze the spectrum of light emitted during atmospheric entry, revealing the elemental composition of the original object and the physical processes occurring during its destruction. High-speed cameras and radar systems can track meteors throughout their atmospheric passage, documenting how they fragment and decelerate as they encounter progressively denser air. These observations reveal that meteoroid disintegration is far more complex than simple melting or ablation, involving intricate interactions between shock waves, thermal stresses, and structural weaknesses that vary from object to object. The most sophisticated studies combine multiple observation techniques to create comprehensive pictures of individual meteoric events. The Chelyabinsk fireball of 2013 was documented by hundreds of dashboard cameras, security systems, and scientific instruments, providing unprecedented detail about how large meteoroids behave during atmospheric entry. The analysis of this event revealed new insights into the physics of high-speed fragmentation and the effectiveness of Earth's atmospheric protection. Similar comprehensive studies of smaller, more typical meteors continue to refine our understanding of how different types of cosmic debris respond to atmospheric encounter. Each observation adds to a growing database of meteoric behavior that helps scientists predict which types of objects are most likely to survive atmospheric passage and which will be completely destroyed before reaching the ground. This predictive capability has practical applications for assessing the threat posed by potentially hazardous asteroids and for planning spacecraft missions that must survive atmospheric entry. The same physics that governs natural meteoroid destruction also applies to artificial objects returning from space, making the study of meteors relevant to human space exploration and planetary defense efforts. The connection between meteoroid research and spacecraft protection becomes particularly apparent when considering missions to other planets with different atmospheric conditions. Mars, with its thin atmosphere, provides much less protection against cosmic bombardment than Earth, while Venus, with its dense atmosphere and high surface pressure, might destroy objects that would easily survive passage through our own air. Understanding these differences is crucial for planning robotic missions and eventual human exploration of other worlds. The same principles that determine whether a meteoroid will survive passage through Earth's atmosphere also govern how spacecraft heat shields must be designed to protect delicate instruments and human crews during planetary entry. The study of 3IATLAS's behavior as it approaches our Sun provides insights into these same thermal protection challenges. The comet's response to intense solar heating demonstrates how different materials and structures respond to extreme temperature conditions, information that directly applies to the design of spacecraft systems intended to operate in harsh environments. The gradual nature of the comet's transformation allows engineers to observe thermal protection strategies that operate over extended periods, complementing the rapid-fire lessons learned from meteoroid studies. While meteors demonstrate catastrophic failure modes under extreme conditions, comets show how materials can survive and continue functioning even while undergoing significant heating and outgassing. This complementary information from different types of objects helps create a more complete understanding of how matter behaves under the extreme conditions common throughout the universe. Whether we're studying the rapid destruction of meteoroids in our atmosphere or the gradual evolution of interstellar comets near our Sun, we're observing different aspects of the same fundamental physical processes. The universality of these processes means that insights gained from studying objects in our solar system apply to understanding phenomena throughout the galaxy and beyond. The same physics that governs 3IAT LAS's transformation operates in the atmospheres of exoplanets, in the accretion disks around forming stars, and in the violent environments near black holes and neutron stars. This cosmic perspective transforms our local observations into windows onto processes that occur throughout the universe. Every meteor that streaks across our night sky demonstrates principles that apply to planetary formation around distant stars. Every measurement of 3IATLAS's composition reveals information about stellar nucleosynthesis and chemical evolution that extends far beyond our own galactic neighborhood. The philosophical implications of this universality are profound. We're not isolated observers studying distant phenomena, but participants in a vast interconnected system where the same physical laws operate from the smallest scales to the largest. The atoms in our bodies were forged in stellar furnaces and distributed through space by processes identical to those we observe in comets and meteors today. This connection between the cosmic and the personal becomes especially poignant when we consider that the material streaming away from 3IATLAS today might eventually find its way into future planets, atmospheres, and perhaps even living beings elsewhere in the galaxy. The transformation we're witnessing represents not just the evolution of a single object, but participation in the ongoing cosmic cycle that creates and distributes the elements necessary for complexity and life throughout the universe. As 3I/Atlas continues its stately progression toward its appointment with our Sun, carrying within its ancient nucleus the chemical memory of another star, we're reminded that we too are made of such cosmic wanderers. Every atom in our bodies has traveled unimaginable distances through space and time, participating in countless cycles of stellar birth and death before briefly coming together in the forms we recognize as ourselves. The meteor showers that grace our night skies throughout the year serve as gentle reminders of these connections, each streak of light representing the homecoming of material that has journeyed through the cosmos for billions of years. The particles that create these displays have witnessed the birth of stars, the formation of planetary systems, and the slow evolution of the galaxy itself, before finally finding their way to our atmosphere for one brief, brilliant moment of transformation. In just a few months, when 3I/Atlas re-emerges from its hidden passage behind the Sun, we'll discover what changes this ancient wanderer has undergone during its most intense encounter with stellar radiation. Whether it appears as the same dignified visitor we've been observing, or emerges transformed into something altogether more dramatic, its story will continue to unfold against the backdrop of cosmic processes that connect our local observations to the grandest scales of space and time. The mystery of disappearing meteoroids, it turns out, isn't really about disappearance at all. It's about transformation, about the endless cosmic dance of matter and energy that creates, destroys, and recreates the universe in an eternal cycle of change. Every vanishing streak of light above our heads participates in this dance, joining the cosmic symphony that has been playing since the universe began, and will continue long after our Sun has faded to a dim ember in the vast darkness of space. And so we find ourselves perfectly positioned in this cosmic moment, conscious beings capable of contemplating our own origins and connections to the universe around us, watching ancient visitors from distant stars undergo transformations that mirror the very processes that created the atoms from which we ourselves are made. In the gentle glow of 3I/Atlas's tail and the brief brilliance of meteors overhead, we see reflections of our own cosmic heritage, reminders that we are not separate from the universe we observe, but integral participants in its ongoing story of change, transformation, and endless wonder. The mathematics of survival in space environments reveals patterns that extend far beyond our immediate cosmic neighborhood. When astronomers model the trajectories of objects like 3IA TLAS, they're essentially solving the same equations that govern the behavior of matter throughout the universe, from the formation of planetary rings to the dynamics of galactic spiral arms. These mathematical relationships demonstrate a beautiful consistency in how gravity, pressure, and thermal energy interact across vastly different scales. Consider the elegant way that orbital mechanics scales with distance and mass. The gravitational dance that guides 3I Atlas through our solar system follows the same mathematical principles that govern binary star systems, the rotation of galaxies, and even the large-scale structure of the universe itself. It's a testament to the underlying unity of physics that the same equations can describe phenomena occurring across more than 20 orders of magnitude in scale. This mathematical universality becomes particularly apparent when we examine how objects respond to heating under different conditions. The sublimation curves that describe how various ices transform from solid to vapor in 3IA-TLASs. Nucleus apply equally well to the atmospheres of distant planets, the surfaces of moons orbiting gas giants, and the behavior of materials in the extreme environments near neutron stars and black holes. The thermal evolution of cometary nuclei follows predictable mathematical patterns based on the fundamental properties of heat conduction and phase transitions. As solar energy penetrates into 3IA-TLAS's interior, it creates temperature gradients that can be modeled using the same diffusion equations that describe everything from how coffee cools in your cup to how heat flows through the Earth's mantle over geological time. But the real beauty lies in how these mathematical descriptions reveal the interconnectedness of apparently disparate phenomena. The shockwave physics that governs meteoroid fragmentation in our atmosphere also controls the behavior of stellar winds as they interact with interstellar gas clouds. The pressure dynamics that create jets streaming from 3IA-TLAS's nucleus operate in planetary atmospheres, in the accretion disks around forming stars, and in the violent outflows from active galactic nuclei. These connections suggest that the universe operates more like a vast symphony than a collection of isolated phenomena, with mathematical themes recurring across different instruments and scales. The same harmonic relationships that govern the orbital periods of planets around our Sun also appear in the pulsation patterns of variable stars and the oscillation modes of entire galaxies. Recent advances in computational modeling have allowed scientists to explore these connections in unprecedented detail. Supercomputer simulations can now track individual particles through complex, three-dimensional environments, revealing how microscopic processes aggregate to create the large-scale behaviors we observe in comets, planets, and stellar systems. These simulations have revealed that 3IA-TLAS's response to solar heating involves cascading effects that operate across multiple spatial and temporal scales simultaneously. Molecular-level processes of sublimation create gas flows that interact with the comet's gravitational field, which in turn affects the distribution of dust and the formation of jets, which ultimately determine the comet's overall appearance and activity level. The computational power required to model these multi-scale interactions represents one of the most challenging problems in modern astrophysics. Unlike the relatively simple two-body gravitational interactions that can be solved analytically, the behavior of real cometary nuclei involves thousands of interacting physical processes that can only be understood through numerical simulation. The results of these simulations often surprise even experienced researchers. The formation of jets and the development of active regions on cometary surfaces emerge naturally from the interaction of thermal heating with the complex internal structure of the nucleus, creating patterns that would be impossible to predict from simple theoretical arguments alone. This emergent complexity illustrates a fundamental principle that operates throughout the natural world. Simple rules applied consistently across many interacting components, can give rise to behaviors that are far more intricate and beautiful than the individual rules themselves would suggest. The flocking patterns of birds, the formation of weather systems, and the evolution of galactic structure all demonstrate this same principle of emergence. 3. iAtlas provides a remarkable natural laboratory for studying these emergent properties in real time. As the comet's nucleus responds to increasing solar heating, we're witnessing the spontaneous organization of complex flow patterns, the development of structured dust clouds, and the creation of tail features that reflect the underlying physics in visually striking ways. The dust tail itself represents a particularly elegant example of how simple physical processes can create complex and beautiful structures. Each particle in the tail follows its own individual trajectory, determined by the balance between solar radiation pressure and the comet's gravitational attraction. Yet collectively, these particles create sweeping curves and intricate patterns that stretch across millions of kilometers of space. The way sunlight interacts with these dust particles creates additional layers of complexity and beauty. Different sized grains scatter light in different ways, creating subtle color variations along the length of the tail that reveal information about the size distribution and composition of the particles. The polarization of scattered light provides additional clues about the shape and structure of individual dust grains. These optical effects transform 3iAtlas's tail into a natural spectrometer, where the properties of microscopic particles are revealed through their collective interaction with sunlight. By carefully analyzing the color and polarization patterns in the tail, astronomers can infer properties of the dust that would be impossible to measure directly, even with the most sophisticated space-based instruments. The European Southern Observatory's Very Large Telescope has been particularly successful in these detailed optical studies, using its advanced polarimetric capabilities to map the three-dimensional structure of the comet's dust environment. These observations reveal that the tail is not a simple uniform structure, but rather a complex layered system where different types of particles occupy distinct regions. The temporal evolution of these structures provides additional insights into the physics of dust emission and transport. Time-lapse observations show the tail developing and changing over periods of days and weeks, with new features appearing and evolving as fresh material is expelled from the nucleus. These changes reflect the varying activity levels on different parts of the comet's surface as it rotates and as solar heating penetrates to different depths. The correlation between the comet's rotational period and the development of tail features provides direct evidence for the existence of discrete active regions on the nucleus surface. As these regions rotate into and out of sunlight, they create periodic variations in dust production that propagate outward through the tail like waves spreading across the surface of a pond. This temporal variability adds another dimension to the already complex physics of cometary dynamics. Understanding how activity patterns change over time requires careful coordination of observations to capture the comet at different rotational phases and under different solar illumination conditions. The international nature of the observational campaign studying 3iAtlas reflects the global interest in understanding these processes. Telescopes in Chile, Hawaii, Spain, and other locations around the world are coordinating their observations to maintain continuous coverage as the comet moves across the sky and as Earth's rotation carries different observatories into and out of darkness. This coordination represents a remarkable achievement in international scientific cooperation, with researchers from dozens of countries contributing data and expertise to create the most comprehensive study of an interstellar comet ever undertaken. The shared excitement about 3iAtlas transcends national boundaries and demonstrates how scientific curiosity can unite people around common goals. The data being collected during this campaign will provide material for research studies for years to come. Each night's observations add to a growing archive that documents the comet's evolution in unprecedented detail, creating a resource that future researchers will mine for insights into cometary physics, interstellar chemistry, and the behavior of matter under extreme conditions. The archival value of these observations is particularly important, given the transient nature of 3IATLAS's visit. Unlike periodic comets that return every few decades or centuries, our interstellar visitor will never again pass through the inner solar system. Every observation is therefore unique and irreplaceable, making the comprehensive documentation of its passage a high priority for the astronomical community. The technical challenges involved in maintaining this observational campaign are considerable. Coordinating observations across multiple time zones requires careful planning and communication between research teams. Weather conditions, instrument failures, and competing observational priorities all complicate the effort to maintain comprehensive coverage. Despite these challenges, the campaign has been remarkably successful in documenting 3IATLAS's behavior as it approaches its solar encounter. The wealth of data being collected is already revealing new insights into cometary physics and providing crucial constraints on theoretical models of how interstellar objects behave in planetary systems. The success of this campaign also demonstrates how modern astronomy has evolved into a highly collaborative and technologically sophisticated endeavor. The days of solitary observers working in isolation are long past, replaced by international teams using networks of advanced instruments to tackle questions that would be impossible to address through individual efforts. This collaborative approach extends beyond the immediate scientific community to include amateur astronomers, citizen scientists, and educational institutions around the world. Many of the most spectacular images of 3IATLAS have been captured by dedicated amateur observers using relatively modest equipment, but applying careful technique and timing. The participation of amateur astronomers in professional research programs represents one of the most positive developments in modern astronomy. Advanced digital cameras and computer-controlled telescopes have made it possible for dedicated amateurs to contribute meaningful data to scientific studies, particularly for monitoring programs that require frequent observations over extended periods. The images and measurements contributed by amateur observers complement the more specialized data collected by professional observatories, filling in gaps in temporal coverage and providing additional perspectives on the comet's behavior. This collaboration between professional and amateur astronomers enriches the overall scientific return from the observational campaign. Educational institutions have also played important roles in the 3IATLAS campaign, with students and faculty at universities and colleges around the world contributing observations and analysis. These educational partnerships provide valuable training opportunities for the next generation of astronomers, while simultaneously advancing our understanding of cometary physics. The involvement of students in active research projects like the 3IATLAS campaign demonstrates the value of experiential learning in scientific education. Rather than simply reading about astronomical phenomena in textbooks, students can participate directly in the discovery process, making their own observations and contributing to the advancement of human knowledge. This educational dimension of the 3IATLAS campaign may ultimately prove to be one of its most important legacies. The students who participate in observing and analyzing this interstellar visitor are gaining first-hand experience with the methods and excitement of scientific research, potentially inspiring some of them to pursue careers in astronomy or related fields. The timing of 3IATLAS's arrival during an era of unprecedented technological capability and international cooperation has created a perfect confluence of circumstances for scientific discovery. Never before have we possessed such powerful instruments, such sophisticated analysis techniques, and such effective means of coordinating observations across the global astronomical community. This technological revolution in astronomy continues to accelerate, with new instruments and capabilities being developed and deployed at a rapid pace. The James Webb Space Telescope, which has provided such detailed spectroscopic analysis of 3IATLAS, represents just the beginning of a new generation of space-based observatories that will transform our understanding of the universe. Ground-based astronomy is also experiencing a renaissance, with extremely large telescopes under construction that will provide unprecedented resolution and sensitivity for studying faint and distant objects. These new facilities will enable detailed studies of interstellar objects that would be impossible with current instruments, potentially revealing entire populations of cosmic wanderers that remain undetected today. The technological advances driving these improvements extend far beyond astronomy itself, drawing on developments in materials science, computer technology, artificial intelligence, and engineering. The same innovations that enable more powerful telescopes also find applications in medicine, communications, environmental monitoring, and countless other fields. This cross-pollination between astronomy and other disciplines illustrates how scientific research often produces benefits that extend far beyond its original goals. The techniques developed for analyzing 3IA-TLAS's spectrum may eventually contribute to advances in atmospheric science, materials research, or planetary defense strategies. The computational methods being refined through studies of cometary dynamics have applications in weather prediction, climate modeling, and the design of spacecraft trajectories. The image processing algorithms developed for astronomical observations find uses in medical imaging, industrial quality control, and autonomous vehicle navigation. These broader applications of astronomical research demonstrate its value to society beyond the pure satisfaction of curiosity about the universe. While the immediate scientific goals of studying 3IA-TLAS focus on understanding cometary physics and interstellar chemistry, the methods and technologies developed in pursuit of these goals often prove valuable in unexpected ways. The economic benefits of astronomical research, while sometimes indirect and long-term, can be substantial. The technologies developed for space-based observations have contributed annually. The Inspiration observation systems that provided to advances in satellite communications, GPS navigation, weather forecasting, and Earth billions of dollars in economic value provided by astronomical discoveries like 3IA-TLAS also has intangible but real value for society. The images of this ancient wanderer from another star system capture public imagination and demonstrate humanity's capacity for exploration and discovery, potentially inspiring young people to pursue careers in science, technology, engineering, and mathematics. The philosophical and cultural impact of astronomical research extends beyond its practical applications to touch fundamental questions about humanity's place in the universe. 3I Atlas serves as a tangible reminder that our solar system is part of a larger galactic community, connected to other stellar systems through the exchange of matter and energy across vast distances and time spans. This cosmic perspective, fostered by astronomical research, may ultimately prove to be one of its most valuable contributions to human civilization. Understanding our place in the universe helps provide context for terrestrial concerns and challenges, potentially fostering a more cooperative and long-term perspective on global issues. The study of interstellar objects like 3IA-TLAS also raises profound questions about the prevalence of life elsewhere in the universe. If comets can carry complex organic compounds between stellar systems, they might also transport the chemical precursors necessary for life, potentially seeding planets throughout the galaxy with the raw materials for biological evolution. This possibility, while highly speculative, illustrates how astronomical research can illuminate questions that extend far beyond the immediate objects of study. 3I Atlas is simultaneously a messenger from the past, carrying information about conditions that existed billions of years ago, and a potential harbinger of future discoveries about life and complexity throughout the cosmos. As we prepare for the comet's disappearance behind solar glare and its eventual re-emergence in December, we're reminded that scientific discovery often involves periods of patient waiting, punctuated by moments of dramatic revelation. The months ahead may bring unexpected developments as 3IA-TLAS undergoes its most intense solar heating, potentially transforming from a well-behaved visitor into a spectacular celestial display. The uncertainty surrounding what we'll find when the comet re-emerges adds an element of suspense to its story that reflects the fundamental nature of scientific exploration. Despite all our sophisticated instruments and theoretical models, the universe retains the capacity to surprise us, reminding us that there's still much to discover about even the most basic physical processes. This element of surprise and discovery is part of what makes astronomy such a compelling field of study. Each new observation has the potential to reveal unexpected phenomena or overturn established theories, keeping researchers constantly alert for developments that might reshape our understanding of the cosmos. The story of 3I Atlas, from its initial discovery through its upcoming solar encounter and eventual departure back into interstellar space, embodies the excitement and uncertainty that drives scientific exploration. Every measurement and observation adds another piece to a cosmic puzzle that connects our local environment to processes operating throughout the galaxy and beyond. The story of 3I Atlas becomes even more enchanting when we consider the remarkable precision required for its discovery in the first place. Imagine, if you will, trying to spot a single snowflake drifting through a vast cathedral while wearing sunglasses and standing several kilometers away. That's roughly analogous to the challenge faced by the ATLAS telescope team when they first detected this ancient wanderer against the star-filled backdrop of the southern sky. The detection itself relied on what astronomers call differential imaging, a technique that compares photographs taken of the same patch of sky at different times. Stars remain fixed in their positions, creating identical bright spots in successive images. But moving objects like asteroids and comets reveal themselves by shifting slightly between exposures. It's rather like playing an enormous cosmic game of spot the difference, where the prize for winning might be discovering a visitor from another star system. But the real artistry lies in distinguishing between ordinary solar system objects and truly interstellar visitors. Most moving dots detected by survey telescopes turn out to be familiar residents of our cosmic neighborhood, asteroids orbiting between Mars and Jupiter, or comets returning from the outer reaches of our own stellar domain. Identifying something genuinely foreign requires careful analysis of its trajectory, looking for the telltale signs of hyperbolic motion that indicate an object unbound by our sun's gravitational embrace. The mathematical calculations involved in this trajectory analysis are beautifully elegant, relying on principles of celestial mechanics that have remained unchanged since Newton first described them centuries ago. Yet the precision required pushes these classical methods to their limits. Determining whether an object is merely visiting from the outer solar system or arriving from interstellar space often depends on measurements accurate to fractions of an arcsecond. Angular differences so small they would be invisible to the unaided eye, even under perfect viewing conditions. This precision becomes even more remarkable when we consider the vast distances involved. 3I Atlas has travelled for hundreds of millions of years to reach our solar system, covering distances so immense that light itself, the fastest thing in the universe, takes years to traverse similar spans. The fact that we can detect such an object at all, let alone determine its origin and predict its future path, represents a triumph of human ingenuity and technological capability. The gravitational environment that 3I navigates as it approaches our Sun creates its own fascinating dynamics. Unlike the relatively simple two-body problem of a planet orbiting a star, the comet's path is influenced by the gravitational fields of all the major planets, creating what mathematicians call a many-body problem of extraordinary complexity. Each planetary encounter, however distant, imparts subtle changes to the comet's trajectory that accumulate over time. Jupiter, with its enormous mass and strategic position in the outer solar system, plays a particularly important role in shaping the paths of visiting objects. Many comets that venture into the inner solar system have their orbits dramatically altered by Jovian gravitational encounters, sometimes being ejected from the solar system entirely or captured into shorter orbital periods. 3I Atlas will experience its own gravitational dance with Jupiter, though its high velocity and specific trajectory will limit the magnitude of any orbital changes. The delicate balance of forces acting on our interstellar visitor creates what physicists call a dynamical system, where small changes in initial conditions can lead to dramatically different outcomes over time. This sensitivity to initial conditions, often referred to as chaos in mathematical terms, means that predicting the exact long-term fate of 3I Atlas requires extraordinarily precise measurements of its current position and velocity. The observational techniques used to track the comet's motion have evolved dramatically over the past few decades, taking advantage of advances in digital imaging, computer processing power, and global communication networks. Modern astrometric measurements can determine positions accurate to thousandths of an arcsecond, precision that would have been unimaginable to earlier generations of astronomers working with photographic plates and mechanical measuring devices. And so, dear stargazer, as we reach the gentle end of tonight's cosmic journey, we've traced the remarkable story of 3IA TLAS, our ancient visitor from beyond the stars, and discovered how it connects to the everyday mystery of why space rocks vanish so dramatically in our protective atmosphere. We've seen how the same beautiful physics that will transform our interstellar wanderer during its hidden passage behind the sun also governs every streak of light that graces our night sky, reminding us that we're all made of the same cosmic dust, all participants in the universe's endless dance of creation and transformation. Sweet dreams, fellow traveler, and may you carry with you the wonder that somewhere out there, ancient messengers from distant stars are still finding their way home. Carry with you the wonder that somewhere out there, ancient messengers from distant stars are still finding their way home.